2.1. In chapter 2, we're going to start looking at defining the derivatives and then the rate of change in terms of limits. In chapter 1, we sort of like guessing ideas, right? Using the guessing idea to find the slope of the tangent line. And later in chapter 1, we learn the ideas, the limit. So now what we can do is using the idea of the limits to compute the slope of the tangent line. You don't need to, sort of like guessing by plugging in the points anymore. So for example, the slope, if I want to find the slope of the tangent line at points A and f of A on the graph, right? That's f of A, of the functions f, then what we can do is we can use the same idea as before. We can use the slope of the secant line, which is from A to f, A to x. So this will be f of x, this point. And then as we move this, point getting closer and closer to A, meaning as x approaches to A, then the slope of the secant line will eventually become what? The slope of the tangent line. So that's why we can formulate the slope of the tangent line, right? And one way is limit as x approaches to A of f of x minus f of A divided by x minus A, which is basically what? The slope of the secant line, y2 minus y1 over x2 minus x1. And another format of this can be written as in terms of h. So instead of we, talking about A to x, we will say that from A to a certain distance h. So therefore A to A plus h. So the function value become f of A and also what? F of A plus h. And that with using those 2 points, right, to draw a line that will become the secant line. So the slope of the formula for the secant line become f of A plus h minus f of A all over, technically it should be A plus h minus A. But minus A and then plus A will become what? Cancels out and you will only get what? H. So that's where this h is coming from. So another way of saying is instead of using x, we're using h as a distance from A to anywhere, the point. And as this distance h is getting smaller and smaller, means A plus h tends to go to what? A. That means the value of h is what? Become 0. Right? Very, very close to 0. So that's why when we say that we will use the limit as h approaches to 0. So this is another format of finding the slope of the tangent line. So on the test, on a homework, doesn't matter which format you wanted to use it, it's perfectly fine. And remember that, this is pretty much what we have done in pre-calc and then maybe some algebra course, finding out the difference of quotient. Right? So that's why, back in pre-calc in my class, I mentioned it. We really need to know how to simplify difference of quotients very well because we're going to use that in Calc 1. So now knowing a definite, how to find out the slope of the tangent line using the limits, let's try to take a look at the example. Example 1, we want to find the equation of the tangent line to the curve of the function f at exactly at what? 2. Because there could be many, many tangent lines that you can find, but at that particular point, x equal to 2, what is the tangent line? So what we need is, first, we need to find out the slope of the tangent line at 2. So the slope of the tangent line. So that will be limit as x approaches to 2, right? Because that will be my value that we want to find at the point where we want to find out the slope of the tangent line. So this is, I'm basically using this first formula right here, formula number 1, okay? Then this will become what? F of x minus f of 2 over x minus 2. So this will give us, when we start computing it, right? And f of x is the same thing as before, which will be 2 minus 3x to the second power minus f of 2, evaluating it, so 2 minus 3 times 2 squared, all over x minus 2. So what we want to do is we want to simplify this. So this will give us negative 3x to the second power, 2 minus 3 times 2 squares, which is 4, 12, negative 10, that will be positive 10, plus 2 will be plus 12. And then x minus 2. Now, this is a rational functions. Direct substitutions cannot apply because what? This as the number that we are approaching to, right? X approaches to 2 is not the domain of this rational function. So what we need to do is using the trick in, little trick in limits. We're going to simplify the function first by factoring out. You factor negative 3 out, so it will be x squared minus 4. So this difference of 2 squared, so x minus 2 and then x plus 2. Now, when we simplify this, that will become x approaches to 2. That will be negative 3 times x plus 2. Now we can use the direct substitutions, which will become negative 3 times 2 plus 2. That will give us negative 12. Now that we got the value negative 12, right, for the slope of the tangent line, then we can find out where the point is, right? So we know that x is equal to 2. So therefore, what? That implies f of 2, which is going to be 2 minus 3 times 2 squared, which will be negative 10. So we have the slope of the tangent line at negative 12. And we want to find the equation of the tangent line at this particular point, 2, negative 10 on the function. So we have a slope and we have a point, so I can use this point slope form to find out what is my equation of the line. That will be y minus negative 10 equal to negative 12 times with x minus 2. So this gives us y plus 10 is equal to negative 12 x plus 24, and subtracting 10 on both sides, which will give me 14. So this is the equation of the tangent line at the point 2, negative 10 on the curve of the functions 2 minus 3x squared. Now, let's take a look at our next example. So for this example, we want to find the tangent equation of the tangent line to the curve of a piecewise defined function at the point 2, 6. So first of all, I need to even, making sure that this point is even on this piecewise defined functions or not. So when I plug it in 2 for x, which is go along with this part of the domain, so that will be using this formula. So 2 to the second power is 4, 4 plus 2 is 6. So therefore, yes, the point is on the curve. So we make sure that. But now, to find out the slope of the tangent line at 2, now notice that the 2 is what? In the both part of the restricted domains in the piecewise defined functions. So that basically is saying that what we need to find out, left-hand side limit and right-hand side limits, because the slope of the tangent line, right, as limit as x approaches to 2 of f of x minus f of a over x minus a in this case, which I should say that, f of 2. And because of the functions, x approaches to 2, I have what? in both of the restricted domains, right? We need to make sure that left-hand side limit and right-hand side limit are the same in order to have what? The slope of the tangent line right here. So therefore, starting with limit as x approaches to 2 from the right-hand side, let's work on that. And that will become f of x minus f of 2 over x minus 2, and which is limit as x approaches to 2 from the right-hand side. Okay. Now, from the right-hand side, the functions f of x is using on right-hand side is what? This restricted domain. So we have to use what? This formula for the functions. So that will become 4x minus 2 minus f of 2. This is functions evaluating at 2. The functions can only evaluate at 2 on the first formula. That's the part that you have to be careful. So therefore, when we write it down, that will be 2 to the second power minus plus 2. Right? So now, when we simplify the limits as x approaches to 2 from the right-hand side, that will become 4x. 2 squared is 4, plus 2 is 6, negative 6, so it will be minus 8. X minus 2. Direct substitution is not applicable, so I'm going to use the simplifying idea. So I'm going to factor it out, which will allow me to simplify the factor x minus 2. So we got from here the limit as x approaches to 2 from the right-hand side. That will become 4. So limit of a constant is a constant, so I have my limit. Right? So now, similarly, next part, I'm going to try to find out the limit as x approaches to 2 from the left-hand side this time of the functions minus f of 2 all over x minus 2. So in this case, limit as x approaches to 2 from the left-hand side. My function, since we are talking about from the left-hand side, right? From the left-hand side of 2, that is fall within this restricted domain. So we will be using this formula for the function, which is x squared minus 2, x squared plus 2, my bad, minus functions evaluating at 2, so it will be 2 squared plus 2 all over x minus 2. So now this will help us to get limit as x approaches to 2 from the left-hand side. X squared, 2 to the second power is 4 plus 2 is 6, so plus 2 will be negative 4 all over x minus 2. Similarly, direct substitutions cannot apply. So what I will do is I will use what? Simplifying idea, factor it out my difference of 2 squared. So which will give us limit as x approaches to 2 from the left-hand side of x plus 2. Now direct substitution is applicable, so which is 2 plus 2, that's give us what? 4. Because of the limit, left-hand side limit and right-hand side limits are the same, now I can conclude that the slope of the tangent line is what? Equal to 4. Okay. Now I have the slope of the tangent line, right? At that particular point is 4, and we have a point 26. So therefore, I can use the point slope formula to find out the tangent line, equation of the tangent line. So that will be y minus 6 equal to 4 times x minus 2. So that will give us y is equal to 4x. Negative 8 plus 6 will be 2. So that will be my final answer for equation of the tangent line in this case. Now, let's take a look at on the next example. So this time, we want to find the equation of the tangent line to the curve of cube root of x at the origins 0, 0. So when I find out the equation of the tangent line, slope of the tangent line, that will be what? Limit as x approaches to a. In this case, my a is what? 0. Okay? For the functions f of x minus f of 0 all over x minus 0. So that's basically using the first part of the formula. So I've been using this formula for like, a couple of times already in the last 2 examples. So let's try to use the second example, second formula. Right? So in second formula, because you're going to get the same answer, I just want to show you variations. So for the second formula, that will be limit as h approaches to 0 of f of a minus f of a plus h. Oh, my bad, sorry. The other way around. F of a plus h minus f of a all over h. So clearly I already, from the previous formula when I write it out, I already find out my a is what? 0. So therefore, in this case, that is basically talking about limit as h approaches to 0 of f of 0 plus h minus f of 0 all over h. So that's basically what's going to happen. So when I substitute it, into the functions, the limit as h approaches to 0, f of h, that is basically what? H to the 1/3 power minus f of 0. When I substitute 0, 0 to the 1/3 power is 0 all over h. So this give us, limit as h approaches to 0, right, of what? 1 over h to the 2/3 power. Right? H to the 2/3 power. Now, consider this as, right, as h is going to what? Getting closer and closer to 0, 2/3 power, that would be a very, very tiny number. See, before in at the end of 1.5, I asked you to write in descriptive form of like, this kind of situations, right? So right now, what we want to do is we want to just like mentally think about it because we have practiced it enough. Now we can think about mentally 1 divided by a very, very tiny number. That will give me what? A very large positive number. So therefore, this is basically talking about what? Going to infinity. Okay? And what does that basically talk about when it's going to infinity? It's sort of related to what? Vertical line. Meanings what? The slope of the tangent line does not exist, right? The limit does not exist. So that means the slope of the tangent line is not defined. So if we have some sort of like undefined slope, we sort of know that it will be what? A vertical line. So therefore, the equation of the tangent line in this case, right? So in this case will be what? X is equal to 0. A vertical line passes through 0. Now, I purposely choose this because like, this is one of the scenario that you may get. The slope of the tangent line is a vertical line. Because if you look at the cube root graph, the function is going like this. Right? So there is a vertical tangent line at this point right there. Right? Because remember, cube root graph means ought to graph like this, right? It has to be a curve like this. So there is a vertical tangent line. And that's what indicating. So far I give you, examples of when the slope is the slope of the tangent line is defined at that point, meaning the limit exists. Now the limit does not exist case, but going to infinity, which related to what? Vertical tangent line. And then let's take a look at on the next example when the limit does not exist. And then there's no tangent line. So in this case, we want to find out equation of the tangent line to the curve of the functions of absolute value at origin again. Right? So if we are working on this, then first we need to think about this functions f of x, that is, x if x is greater than 0, right? 0 if x is equal to 0, and negative x if x is what? Less than 0. And we want to find out the limit as the slope of the tangent line, that is the limit as x approaches to my point A is right here, right? Which is 0 of the functions, right? Which is f of x minus f of a all over x minus a. So that is basically talking about the limit as x approaches to 0 of absolute value of x over x, because f of 0 is still 0. Now, in order to talk about this absolute value of x to the limit as x approaches 0, now we need to what? Look at the left-hand side limit and right-hand side limit, because the limit that we approach into is what? Within the more than one part of the restricted domain. So if I say that the limit as x approaches to 0 from the right-hand side, right, of the functions, so which is on this top part, from the right-hand side, which is going to be what? We are talking about this part, will be x over x, which give us limit as x approaches to 0 from the right-hand side of 1, limit of a constant is constant. If I find out the limit as x approaches to 0 from the left-hand side, then that will become my absolute value from the left-hand side is what? This restricted domain. So this will be negative x over x, which is the limit as x approaches to 0 from the left-hand side of negative 1. That will be negative 1. And notice that the left-hand side limit and right-hand side limit, they are not the same. So that tells us this limit is what? That's not defined in any. Right? It's not question mark anymore. Now we found out that it's not defined. So when the limit does not define, right? It's not infinity like the last case. This one is the limit that's not defined. And that basically tells us there's no slope of the tangent line, right? So if you don't have the slope, then you cannot find the equation of the tangent line. So now this conclude that, right? No tangent line at what? 0, 0 for this function. Now, if you take a look at on this graph, its absolute value of x is a V shape. At 0, 0 right here, that's origin of 0, 0. And the reason why we said that, we found out that the limit does not exist is because at that point, I can have a tangent line that's like this, horizontal, or I can have a tangent line like this, or I can have a tangent line like this. Notice that I have infinitely many tangent lines that I can draw at that point. Right? So you won't be able to find, a specific slope of the tangent line value right there, right? Because there are so many of them. So from here, right, one thing that we can I can help you to conclude, and then you can read more about it. It is in the textbook somewhere, right, in this chapter. When the graph has like, a sharp corner, something like this, or a sharp corner like this of functions, like that, and we will not be able to find the slope of the tangent line at that point, right? Because there are so many of them. So that's something that you can remember. So this is an example of what? No slope of tangent line, right? No tangent line in this case. Now that we know how to find out the slope of the tangent line, right, of any a curve at a particular point, right away we want to relate it to what we learned in 1.4, which is slope of tangent line can be interpreted as instantaneous rate of change, or in that sessions 1.4 we particularly look at what a position functions and then the rate of change of the position function, which is what a velocity. So we can also find out the instantaneous, rate of change on the positions, which is instantaneous velocity, as the same formula as we did, right, in the slope of the tangent line, finding the slope of the tangent line. So average velocity, we know that displacement divided by the time, that is what equivalently, interpreting it as the slope of the secant line in 1.4, which is f of a minus h, right? F of a plus h minus f of a divided by h. Now, if we want to find out the instantaneous velocity, when we talk about velocity at a certain time, that is instantaneous velocity, then we're going to use the limit idea, right, by denoting v of a, right, instantaneous velocity at a particular time a, or velocity at particular time a. That will be limit as h approaches to 0 of f of a plus h minus f of a divided by h, right? So we don't have to guess it like in 1.4 anymore. We have a formula to be able to find that out. So let's try to take a look at and then do these problem. First, we want to find out a velocity, right? A rock is thrown upward and its position functions after time, after t seconds is given to us. S of t is equal to t squared minus 2t. And we want to find the velocity of the rocks when t is equal to a. So to find this problem, part A, right? Part A, the velocity functions at a particular point A, that is basically what? Limit, we are looking for a limit as h approaches to 0 of f of a plus h minus f of a all over h. In this case, I want to change it according to the problem. This is not f functions anymore. We have what? A position function s. So a position function s, right? Make sure you write it properly. So now, computing this limit as h approaches to 0 of brackets, and we're going to be substituting a plus h into the s function, which is going to be a plus h squared minus 2 times a plus h, close bracket, minus the functions evaluating at a will be what? A squared minus 2a all over h. So continue simplifying this part, right? Continue simplifying this part. That will give us the limit as h approaches to 0. FOIL it, that will be a squared plus 2ah plus h squared, distributing -2 and distributing negative to the next functions. We got that. Simplifying a little bit further, that will give us limit as h approaches to 0, right? A squared cancels it out. Minus 2a and plus 2a cancels it out. I have 2ah plus h squared minus 2h. And we want to reduce with h, factor h, so I'm going to factor right away. So it'll be 2a plus h plus minus 2 over h. So finally, this gives us limit as h approaches to 0 of 2a plus h minus 2. Direct substitution is applicable at this point. So when I substitute 0 for h, and then we got the velocity functions, right? The velocity functions, which is 2a minus 2, and that is the part A. Right? So v of a in general. Since a is an arbitrary number, so we can talk about what? The time at any second. Now, part B, we want to particularly look for the velocity at what? 1.5 second. So that's basically talking about what is v of 1.5. Okay? What is v of 1.5? Since we already know the velocity functions, right, at any points and at any times a. So if 1.5 second, all I have to do is what? Substitute it for a with 1.5 minus 2. 3 minus 2, that will give me 1. So what do we get? This is basically what? The velocity unit per second. Okay. Part C. When will the rocket hit the surface? So this is more of like, the problem that we did in algebra. So the rockets go up and then come back down and then hit the surface. That means your positions will be what? 0 again, right? And then we want to know what is the time, how long does it take, right, to hit the surface again. Remember, this rock is like thrown upward. So in this case, basically what we are asking for in this case is what? One S of t is equal to 0, right? That's what means hit the surface. And what is my t is going to be? So we have a function S of t is equal to what? T squared minus 2t. And when S of t is equal to 0, what is my function going to be? So that is basically t is either 0 or 2. Right? And t equal to 0 is initial point. It's not hitting back to surface. So therefore, my answer must be what? 2 seconds. So interpretation will be after 2 seconds, right? The rock will hit the ground. And why do we want to do that? Because of part D. Take a look at on the questions on part D. Part D asks you, what velocity will the rock hit the surface? Because we want to know instantaneous velocity at that moment. So basically we are looking for what? Velocity at 2 seconds. So that will be 2 times 2 minus 2, which is 4 minus 2 will give me 2. So that basically talk about what? The rock will hit the surface at 2 units per second. So because of I didn't mention about what is the velocity, what is the position functions representing in terms of foot or inches. So we would just say that what? Unit per second. That's velocity. Okay. So with this example, right, you can try yourself on example number E, the next example, right? Pause for a second and then try it out and then check the answer with me. So TTC jump from the top of 400 feet side skipper, and the positions function S after t second is given by S of t equal to 400 minus 16 t squared. So part A is asked to find the average velocity during the time interval of 1 to 2 seconds, between 1 and 2 seconds. So average velocity is basically what? Change in position divided by change in time. So change in position is S of t, right? S of 2, which is a 2 second, minus S of 1 second, what are those positions, divided by what? Times ellipse, which is 2 minus 1. So when you use a calculator and compute that, right? So 400 minus 16t squared, 336, 400 minus 16, 1 squared, that'll be 380. And then when you subtract it, that'll give us what? 48. So this is a negative value, right? 48. So That's basically what going the down directions. That's what basically this negative means, right? Now, find out the velocity at t equal to 3. So you're going to have to use what? The limit. So try that, and then let's check. So velocity at instantaneous velocity at 3 seconds. So we use the limit formula, right? The formula limit as h approaches to 0 of s of 3 minus 3 plus h minus s of 3 all over h. Evaluate it into the s functions, and we got 400 minus 16 times 3 plus h quantity square minus 400 minus 16 times 3 square. Simplifying that, right? FOIL it, distributed the negative correctly, and then after reducing the factor h, we got limit as h approaches to 0 of negative 96 minus 16h. Direct substitution is applicable at that point. So when I substitute, 0, we got negative 96 feet per second. So after 3 seconds, this is the speed of falling down, right, from the 400 feet side script. So as you can see, right, from chapter section 1.4, we can relate the slope of the tangent line with the instantaneous velocity. And the instantaneous velocity is only one of the many applications from the real life problem, right? There are many natural sciences, like, in natural sciences that we want to use that situations, like, that formula. For example, if you are talking about, in a chemical reactions, you want to know instantaneous rate of change of the chemical reactions at that particular time. So, and then also, like, in the populations, we want to find out, what is the population growth, the rate of change at that moment of a colony of bacteria. So that rate of change, like, is not only used in this precision functions, it's used in many natural sciences, and then some other application. So this formula is basically very important. So now what we want to do is, we want to give a name for that formula, and we want to make a definitions out of it. And it is called the derivatives. The derivative of the functions at a number a, because in this section we're going to look at, like, at a particular point a, will be denoted by f prime of a. That's how we read, right? F prime of a. So the derivative of a functions at a is called f prime of a, and then the formula is defined to be, what we just learned earlier, limit as x approaches to a of f of x minus f of a divided by x minus a, or we can also use another formula, which is limit as h approaches to 0 of f of a plus h minus f of a divided by h. So from now on, you need to be careful, because later on we're going to be learning how to take the derivatives of a functions, right, as a functions, not as a particular point, right, as a functions in a shortcut format with the formulas. But on the test, if I ask you find the derivative of functions by using the definitions, then you're going to have to simplify this limit and then try to get that. So that's a big difference. Okay, so extra be careful on reading the questions when you're taking the test. So let's take a look at on example A. Find the derivative of the functions at A, right, for what the function is x to the third power. So either formula is fine, whatever you want to use, but let's start with the proper notations. F prime of A is a little bit tilted, right? Not straightforward. So this is basically limits as x approaches to a, right, particular point at that particular functions. Another way of saying is we want to find out instantaneous rate of change at that point of the function. And this will become, right, f of x minus f of a all over x minus a. So I'm using the first formula. Then this will become, when I substitute it, a proper functions, that will be x to the third power minus a to the third power and x minus a. And remember how to factor difference of two cubes, right? Then it will make it easier for you. Otherwise, you're gonna go crazy, right? So x minus a and then x squared plus ax plus a squared all over x minus a. So by factoring out, this helps us to compute a lot easier, right? Simplifying it because direct substitution cannot apply in the original problem. Because when I substitute a, then it will become, it's not part of the domain of the rational function that we're looking at. So this will become x squared plus 8x plus a squared. And when now the direct substitution is applicable, so it'll be a squared plus a times a plus a squared. So basically we are adding a squared 3 times, so it'll be what? 3a squared is my final answer for this. Let's take a look at on the next example. So this time I'm going to use another formula so that you can see how I use like different formulas on different ones. In general, the bottom line doesn't matter which formula you use, it will be the same answer. Okay, and in this case, f prime of a, I'm going to be using the second formula. So limit as h approaches 0 of f of f of a plus h minus f of a all over h, right? Because we are approaching to, or we are looking at the limit at the particular point a. So now, when I substitute it, limit as h approaches to 0 of square root of a plus h minus 1 minus f square root of a minus 1 over h. So this is like a radical functions, right, that we saw before in simplifying the limits. So you need to remember direct substitution is not applicable. So what we need to do is we need to rationalize the numerator and then see we can simplify or not, right? So let's try to rationalize the numerator and see what we get. So when we rationalize the numerator, we basically multiply by the conjugate factor, exactly the same except the operation now it becomes positive right here, right? And multiplying the numerator and denominator. When you multiply to the numerator, that's difference of 2 square. So the square and square root, they cancel out. So I have a plus h minus 1 minus a minus 1. In the denominator, we multiply the binomial with h. A lot of times, this is the mistake that I usually see because, forgetting putting what? Parentheses around of this. So be careful with that because you are multiplying the binomial with this h right there. So h is a factor by itself. Simplifying the numerator now, that gave us, a, when I distribute the negative on the second grouping symbol, a cancels out, 1 cancels out, so I have h alone by itself on the numerator. And that is the part that it will help us to get rid of the h in the denominator, which, will help us to use the direct substitution now. So finally, this will become the limit as h approaches to 0 of 1 over, because h and h cancels it out, square root of a plus h minus 1 square root minus square root of a minus 1. Now direct substitution is applicable, so therefore it will be 1 over square root of a plus 0 minus 1 minus square root of a minus 1. Basically, plus, my bad, right? Basically, we are adding two of them together, so my final answer becomes 1 over 2 times square root of a plus a minus 1. And that will be my final answer for derivative of a function at particular points at a. Okay. So finally, let's take a look at the last example, which is rational functions 1 over x. Let's try to compute that. So for this last example, C, functions of 1 over x, I'm going to use, when I find derivative of function f at a, we're going to use this formula. Limit as x approaches to a of f of x, in this case, which is 1 over x, minus f of a, which is 1 over a, and divided by x minus a. So simplifying this rational complex fractions, basically what we're going to do is we're going to multiply the numerator and denominator by the LCD of all the fractions, which is ax. So that will give us, on the numerator, when I distribute it, that will become x and x, reduce it. In the second fraction, a and a, reduce it. So I will have ax times with x minus a. And when I simplify this, the limit as x approaches to a of that will become what? Negative 1 over ax. Now the direct substitution is applicable, so it will be negative 1 over a times a, which is my final answer is negative 1 over a squared. And that is the derivative of functions at a for the function as well, 1 over x. Okay. Now that we did all these three problems, right, we want to continue and look at the next example, which is giving you a certain conditions and then try to graph it, right? So, which is this example. So take a minute to read these questions and then we're gonna go over that. So we want to sketch the graph of a function g for which g of 0, g of 2, and g of 4 equal to 0. So this is basically talking about the zero of functions, right? Meaning one where y value is 0, right, for these particular x. So that's zero of functions, or in a graphical format, we interpret it as what? The x-intercept. So my x-intercept will be at 0, at 2, and at 4. Right? Those are x-intercept. So I can sort of see that, like, how this graph is going to be going, right? So if this is x-intercept, then my graph, right, could be, go loop like this, or my graph can loop like this. Right? So these are the situations that I expecting. But I don't know which one. And I don't know how far, this peak is going to be way up here or way down here. We don't know yet. But however, right here, it gives us this at g prime of 1 and g prime of 3 is equal to 0. So what is g prime talking about? The way that we can interpret it is what this is what the slope of the tangent line at those particular points, right? 1 and 3. So the slope of the tangent line is 0. That means like when the slope of a line is 0, that basically talk about what? Horizontal line. So for sure, I know now that my peak should be at 1, right? I should have a horizontal tangent line right here, right here, right here. I don't know. It will be somewhere. And also, it could be what? At the bottom. We don't know. Okay. And then also we have another horizontal tangent line at what? G of 3. So exactly at 3, there will be a horizontal tangent. Right? Either up or down, below axis or below above x-axis. So that's something that we don't know. Right? So our guess of the shape of the loop is correct now, because if there is a horizontal tangent line, I need to either what? Touch it and then come back up, because that will be the peak. because the slope of the tangent line must be what? 0, right? Which is like horizontal line right there. Now, at this point, it will be tedious to graph, but in chapter 3, we will log into more. But I want to make sure you also understand graphical interpretations of the derivatives right now. So I want to show you in events. The next one, let's try to skip these portions for now, and then try to look at the easier one, which is what? Limit as x approaches to 5 from the left-hand side of the function, it is infinity. So that basically tells me I have what? A vertical asymptote at 5. So here is vertical asymptotes at 5. And notice that it is approaching to 5 from the left-hand side, it's go to infinity. So going from this side, right? Approaching from the left-hand side. So we don't do anything from the right-hand side. We don't know. It's never tell us. So now that sort of tells me this part right here, which is this is something that if you took my pre-calc, I always tell you guys to, think about or write it. Even I ask on the test, write it down the descriptions, right, of the behavior when it's close to the asymptotes. So in this case, it's going to positive infinity. That's basically telling me my graph, when it's close to 5 from the left-hand side, is going in this directions. And then the next one, as x approaches to -1 from the right-hand side of the functions, is negative infinity again. So approaches to -1, here is the vertical asymptotes. And this time is approaches to -1 from the right side on this directions, is go to what? Negative infinity. So my limit is negative infinity on this side. So that means the graph's going to be going down like this. So from this behavior around the asymptotes, right, vertical asymptotes, and knowing the 0 of the functions, right, then I can now sort of clearly see that my graph will be like this. Peak, go back down, we'll get some peak, and then go back up. Once again, I don't know how high this peak or how low this peak gonna be, because we don't know, right, any information about that. We are just drawing, right? We are just drawing one of the graph of the families of the graphs, right, with these conditions met so far. Now, let's try to double check with, is that the way that we graph it, is that correct or not, by filling the rest of the information. G prime of 2 is equal to -1. That means the slope of the tangent line at 2, right, on the graph is -2. So that's negative slope. So when I look at 2, yes, notice that my slope, the tangent line, the slope is what? Negative slope right there, right? Negative. And then I look at again, G prime of 0 and G prime of 4, the slope is 1. So G prime of 0, that means the slope of the tangent line at 0, that is positive slope. G prime at 4, that is slope of tangent line at 4, that is also a positive slope. So therefore, this graph that we predicted, the shape is what? Close. So therefore, we will sketch this as our graph of a function that's satisfying what? The following conditions. And once again, we don't know how high this peak and how low this peak is going to be. So notice that I'm using one by one information by one information, put in the easier one first, and then try to visualize how the shape of the graph is going to be, and then check with something using the rest of it. Right? So this is like using the conditions, right, to sketch the shape of the graph of the functions. And let's take a look at more of these, right? A little bit more of these. let's take a look at on these two. So it's giving to you the functions f, and we want to graph the derivative of the functions. Okay. And you can do it on the same graph, but I would like to show it to you this way, so that way, it's a little bit better. So again, x-axis and my y-axis. And first thing that what we want to pay attention on this is, remember, the f prime, right? We can interpret it as what? The slope of the tangent line at particular points on the f functions. So that basically tells me now, notice that this point right here, this point right here, and this point right here has what? The horizontal tangent line, right? Horizontal tangent line. So that tells me on the graph of f prime functions, right? The value of f prime will be 0 because horizontal tangent line, that means what? The slope is 0. So now I can bring it down. Here is a intercept right here on the f prime graph. And here is the intercept, f prime graph. And here's the intercept. See, I basically drag down so that if you graph it on the same axis, then you will be able to use a different color and draw it, right? So I just want to show to in two separate ones so that you can see how I'm going to approach it. So now I got these already. So now what we're going to do is we're going to try to look at each part between these zeros in the f prime. If you take a look at this, everything, the left side of this 0, right? And notice that in the original functions, when I draw the tangent line is what going downward. That's basically talking about the negative slope. So f prime value, which is the slope of the tangent line on this interval, is negative. So that means f prime values are negative value. So that would say that it will be what? Notice that it's going to go steeper and steeper. That means what? A larger negative value, and then going to more shallower the slope, which is smaller the negative value. So that's basically tells me, I will have a negative values on this side. So this is the graph gonna look like. Now, if I look at the interval between here, these two 0, then I will be able to see that. Let me use a different color. Right? Let me use this color right here so that you can see what's happening on the graph. Now I'm going to use a different color. So in between the next 0, this is what? Increasing, right? The slope is like positive slope. But how large the slope go, we don't know. So we can only say that, this is going to be a positive value. And notice that it's a little bit shallower, steeper, and then shallower again. That means a smaller positive value and a larger positive value, and then go back down to smaller positive value. That's the only way that I'm going to be getting going up and then coming back down to hit this x-axis, which is going to be what? The intercept that we're going to get. And then from this point on, you can see that, the slope of the tangent line is what? Going negative again. Once again, the steeper, a little bit shallower, and then so on and so forth. So that's going to go down like this and then come back up, right? Still, all of these are negative value right here, right below the x-axis, negative value. Because negative slope, that means what? F prime value is what? A negative value. And finally, if we look at on this part right here, the last portion is basically what? Going a positive slope right there. So this is basically what a positive slope means. F prime values are positive, so that's above the x-axis, and then it's going to be going like this. So this is basically the f prime graph getting from this f functions, the graph of f functions. Right? So this is a little bit like, much easier case. And then taking a look at on the next one, this one we have to be very careful, right? When we talk about f prime graph. And first, like before, when we look at, the peak, right? And there's one which is going to give us what horizontal uh, tangent line at this 0. So I know that there will be what an x-intercept in the f prime graph. Then let's take a look at on the left hand side and right hand side. On the left hand side, as you can see, this is the slope of the tangent line is getting what steeper and steeper. So that means from the smaller positive value, now it's going to what the larger positive value and then go down to 0. Right? It will go back down to 0 because yeah. So that basically tells me my graph, I cannot graph like from here to like this, because that would tell me what a very large slope and then coming down to a smaller and smaller positive slope. But in this case, it's not going that way. It's going from what a smaller slope, right? Smaller value of slope, and then getting larger and larger because the tangent line is steeper right here, right? The slope of the line is steeper. That means what? The slope is bigger value. And then it go back down to horizontal tangent line. That means what? The slope is 0. So it must be go back down to 0. So that basically tells me I will have what? A smaller x value, and then all of a sudden it will go large and then come back down to what? Reach 0, like this. And then on the other side, it is continuously what? A negative slope. You can see the negative slope, negative slope, negative slope, negative slope, negative slope. But from 0, it will start getting steeper and steeper, which is start increasing negative value. And then all of a sudden it will decrease down to what? More of like a horizontal, close to a horizontal, which means what? Very small negative slope. So that means in this side, from smaller negative value, and then all of a sudden it will go to a larger negative value. And then it will go back down to what? Getting smaller and smaller negative value. Right? So this is basically how the graph of this functions, f prime function is going to look from this given f functions. Right? So you cannot just like graph it all positive or negative. You need to also start thinking about the slope of the tangent line, how the way they slanted. Do they slant like very narrow, like very shallow, or like steeper, and so on and so forth. Okay? And let me give you one last example and then conclude this section, which is the case that we've seen before. So example C, if I take a look at giving you a graph like this, let's say next function graph look like this. Okay. I meant to graph like this to make it easier. So let's say this is f functions. So in this case, when we graphing the f prime functions, and notice that this is a sharp corner at 0. So that basically tells me there is no, we don't have the slope of the tangent line at that point. So that means it will be what? A vertical asymptote, because there is no value at 0. Right? There will be a vertical asymptote. And then when we look at on the left hand side, this will be what? Negative slope, and then getting steeper and steeper. Right? So that basically tells me from the shallow, smaller negative slope to what? Getting a larger and larger negative slope. My graph is going to go like this. I cannot go on the top part because we are talking about negative slope. That means my f prime value will be negative, so it must be below the x-axis, right? So a smaller negative value to become a larger negative value, shaped like this. And on the right-hand side, similarly right here, I will have what? A very large positive number slope, and then it will go down to what? Smaller and smaller positive slope. So that means like, graph look like this. So this is the last example that we want to talk about it, and the homework of this sessions is all the way in the big on the title of this unit, right? So try to do the homework on this part right here.